to take a look at graph theory. In graph theory, I have some subcategories of puzzles and map coloring and things that probably sound like they're not terribly math related. The first step I always take when looking at mathematical concepts is to first determine the vocabulary that I need to use. And a graph would consist of a set of points, which we would call vertices, lines and edges that join up those points. And certain types of graphs can also be called networks. If I look at the two ways to draw the same graph, I can wind up with different figures depending on how I connect the pieces. This is a common example of a bridge problem. Starting at some point, is there a way to visit all the parts of the city by crossing each bridge once and only once? So this is like those social media games where you're trying to get from point A to point B and not overwrite or swipe over what you've already done in a maze. So if I look at the graph model, I can just basically draw this out with a connection of points rather than actually having the full scale image. And so if I wanted to rephrase this and say it in the proper language, I would say, can this graph be traced? To trace a graph means to start at a vertex and draw the entire graph without ever lifting your pencil and never going over the edge more than once. This is sounding more and more like those brain teasers, right? A graph is connected, so if that is possible to travel from any vertex to another vertex by using successive edges or lines, a bridge and a connected graph is an edge that if removed, it shows the graph would no longer be connected. Connected graphs are what we call networks. So if you look at the connected graph, the figures are connected. And a non-connected graph, the figures aren't connected. Nothing connects the triangle to the line segment. A vertex of a graph is odd if its endpoint and an odd number of edges. So a vertex would be even if it is the endpoint and there are an even number of edges. In general, the degree of the vertex is the number of edges that are connected in that vertex. So here's an example. What are the degrees of vertices A, C, and F in the graph? Which of them are odd and which of them are even? So if I look at vertex A, it is the endpoint of two edges, so it would have a degree of 2. And very similar, if I look at C, there are 3 points connecting into C. And if I look at F, nobody's connected at all, so it has a degree of 0. B and C are both odd because they have an odd number of connectors. The others are all even because they have an even number of connectors. Now, what's interesting is, in this situation, we consider 0 to be an even number, even though numerically 0 is not actually even. So let's formalize this with a theorem. If I look at the observations made by these lines, while tracing the graph, I can't begin or end with vertex A, then A must be an even vertex. So I can't start at A, I have to kind of pass through it. If a graph can be traced, then it has to have at least 2 odd vertices. And this would follow directly from 1. A graph can be traced if it's connected and has 0 or 2 odd vertices. And you can get this just from sketching these pieces down. So if I'm looking at an example, which of these graphs can be traced from A, B, C, and D? If I look at A, it's not traceable. So I have several places that are feeding in odd vertices, but I don't have the right ratio of them. What's really weird is C is actually traceable, and I feel like that's the one we're most likely going to look at and say, oh, that's not traceable. Remember, you have to follow the criteria from the previous 3 slides. So if I'm looking at Euler's theorem as a way of solving a problem, you're probably thinking, when would I ever need to play connect the dots with line segments? This is really not about playing connect the dots. It's not about line segments. It's like those brain teaser apps where they're looking to really see, are you critically thinking? And the bridge feature has two features that are present in every graph model. It has a set of objects, which would be my 4 bodies of land, and a relationship among those objects as if they were connected by bridges. If these two features are present in a problem, you could model it with a graph like follows. A path in a graph is a series of consecutive edges where no edge is repeated. So that's an interesting definition. The number of edges in a path is called its length. We are not used to saying length with the number of edges. We are used to measurements. That's going to be a place where you have to rethink around what you have. An Euler path would be one that begins and ends at the same vertex, and it's going to be an Euler circuit. The graph with all even vertices would contain an Euler circuit and would be called an Eulerian graph. Lots of vocabulary in this section, guys. If I'm looking at this star and I want to find some paths, there are many ways that I can get from the vertices to one another. And if you think about this, when you ask people to draw a star, you're going to see people that do things very differently. Now, Fleury's algorithm builds on this even more, and it says a connected graph, meaning that we can get from one figure to another, has all even vertices, and we can find an Euler circuit for it by beginning at any vertex and traveling over those consecutive edges, as long as it follows the two rules below. If I go back to looking at a figure, things can get rather complex but still work under this principle. So let's assume that we're doing maintenance work on these pathways, and these pathways are some type of walkable trail for people. The pathways join A all the way through K within a theme park. If you want to find an Euler circuit in this graph to make your job efficient so that you're not going along the same pathways multiple times, we would assume that I want to leave from building C and return to building C. So if I use this algorithm to find the Euler circuit, the first step is to start at C and traverse the edge CJ, then JK, KI, and IF. These edges are numbered 1, 2, 3, and 4 in the figure, and they indicate the order in which people are going to travel them. We're going to erase these edges and also the vertices because they no longer have any edges joined to them. So I am deconnecting those pieces. Now I'm at vertex F. And I can't go FC because it is a bridge that connects my figure. So I have to traverse FG, GI, IH, and HF as shown by the arrows. And step 3, I don't have any choice but to follow this pattern so that I can accomplish my entire route as intended. So if I look at the final circuit, I'm going to give it in terms of line segment traveling. And I will look at this and say, wow, I really did traverse it with only passing things one time. So when you're doing those brain teasers, this is essentially what you're doing, is trying not to overlap the same path twice. So while you may not feel like that brain teaser is actually math, it actually is. If I want to Eulerize a graph, I would add the edges and convert those to a non-Eulerian graph into an Eulerian graph, which is called Eulerizing a graph. This is a lot of Euler, right, guys? Designing a duck tour. So let's use this example. The Boston Duck Tour wants to design a duck route in a historic area of Boston where they're seen on the map. I want to begin to end the tour at the same location, and I want to minimize traveling over any street more than once. Again, here's that brain teaser problem. Find the route. This is graph theory, which is exactly what those brain teaser apps are asking you to do. So I'm just going to flip through so you can see the different ways that we travel. Another is map coloring, using at most 4 colors. This is graph theory. So if I'm looking at colors, Is it possible to color a map so that any two regions that have a common border would have different colors? This is one of those things where you have to actually do it. So first I have to identify, well, who shares a common border? And then I'm going to work backwards from using vertices and lines to travel and not just having the image. If I look at this, there's no particular rhyme or reason to what's going on, so I just have to do trial and error, and that's how I arrive at my solution. Another use of graph theory would be for scheduling. So we've seen it for geography, we've seen it for paths, and now we have for scheduling. If I'm going to use the table which lists the committees that have common members, and I want to try and find a time to schedule a meeting. To do that, I'm going to create the table that gives me the information that I need as a legend, and then I'm going to recall things that are going to overlap. So in a building the graph model, I must do two things. I can have a set of objects, which in this case would be committees, and the relationship to the objects would be that two committees are related if they have the same members in common. So by members, we're passing through pieces of the vertices.